Good morning, everyone. Thank you for introducing me. So I'm Siham Shanti. I'm a PhD student, and today I'll present 3D printed polymer concrete optimization from insights from early age rheological and mechanical properties. I've worked under the supervision of my postdoc, Dr. Daniel Hiras Morthia, and our advisor, Dr. Mahmoud Ridataha. So in this presentation, we will cover the following topics, starting by 3D printed polymer concrete by design, ending with the application of a 3D printed polymer concrete by design and the full-scale 3D printing of polymer concrete. So polymer concrete is like normal concrete, but instead of using cement, we are replacing it fully or partially with a polymer. And this polymer can be any type, thermoplastics or thermoset polymers like epoxies, vinyl ester, polyester. And you can see here the phases of the polymer concrete. We have the aggregate phase, the polymer phase, and the voids. The interaction at the interface between the aggregate and the polymer, this what makes the mechanical properties of polymer concrete. So in our research, we are trying to follow a comprehensive experimental and in the same time numerical simulation to have a full-scale 3D printed polymer concrete. We start, of course, like polymer concrete mix design, and then we do preliminary assessment and we test the 3D printability. After that, we measure the rheological and the early age strength characterization. We fit the finite element model with the properties we are getting to predict failure. And once we finish modeling the 3D printed polymer concrete process, we can do a full-scale 3D printing. So here's an example of the mix designs. We can design the mixes using different polymers and different polymer weight content. We can have 14% polymer weight content and double it up to 32% polymer weight content. Of course, by playing with the mix design and do the necessary modification, we can increase this or reduce it further. So after we have a number of mixes, we do the preliminary assessment of those mixes, and this is by visual assessment from prior experience in 3D printing. And then we do the slump flow and the slump. We agreed, and based on other work done by others, that mixtures with the slump between 4 and 8 millimeter and a slump flow between 150 and 190 millimeter could give a high surface finish and high buildability. So those mixes that passes the first step then are moved to the next step, which is defining the optimal 3D printing parameter. And this is very important, as you can see the extrusion speed and the extrusion rate significantly influence the printing quality of the filaments. So we, in the same time, we are testing the buildability and extrudability. So we test at different printing speeds and extrusion speeds, and then we qualify this and quantify it by measuring the change of area or the ratio of the printed area to the actual designed area, to the ideal area. And we plot it against a velocity ratio normalized of the 3D printing speed to the extrusion speed. Of course, values closer to 1 would give high dimensional stability. So to select the 3D printing parameter, we will choose, like for example, for the given mixes, we have found that 200 and 300 are the velocity ratios we can work with to give us a dimensional stability or a value of the area printed to the area ideal of 1. The next step comes by testing the printability window. As we know that polymer concrete has a fast hardening rate, like around 60 minutes, 45 minutes. So for that, it's very important to test how much time we have to enable to enable the extrudability and a good dimensional stability. So we managed to increase the burst time or the printability window to up to 7 hours and the 3 hours. Of course, that might have an effect on the static yield stress, the viscosity, and the thixotropic behavior of the material. But that's the next step comes here. We We tested the buildability. The buildability is the material ability to to carry its own weight and the subsequent layer's weight. And the increase of the static yield stress needs to be higher than the given ratio, which is the weight times height divided by the square root of 3. So the first, because we have no standard guidelines to measure buildability, we followed the standard common practice in the literature, which is building 3 layers. So here we are printing 3 layers of 10 layers of polymer concrete, and the other thing to make sure that it can have a good buildability is measuring the height reduction. So we take a continuous video for 24 hours, and then by a computer software we analyze the deformation from the preset height, and then we compare it to the reported values in literature. The polymer concrete was found to have like a comparable result to normal concrete and even less deformation. However, if we increase the polymer weight content, we are experiencing a higher deformation, but it still was buildable, and it gave us the required buildability criteria reported in other work. So then we went a little bit far, and we increased the polymer content up to 70% just to check the buildability without doing any modification. The same mixes were taken and increased the polymer weight content. And immediately after the 3D printing, we started having plastic deformation. The mixes started to buckle. So this is an example of a rejected buildability. Of course, that's all happening because of the rheological behavior of the polymer concrete. The rheological behavior of the polymer concrete highly depends on the aggregate and the polymer type and content. And the big picture is the polymer and aggregate interaction together. Polymers in large have an Newtonian behavior with zero thixotropy and a zero initial shear stress. However, once we start adding aggregate, we start having to see an initial shear stress, and they start having a thixotropy, and the model is then a Birmingham CDS plastic model, and it can be modeled using Herschel-Buckley equation, which is the maximum is the static yield stress with this hysteresis loop here, and the slope is the viscosity, and the y-intercept is the dynamic yield stress. The area between the two curves is the thixotropy. So here's an effect of the polymer weight. Of course, we saw that the polymer weight increased the deformation, and that's because of the decrease in the static yield stress. It's normally the practice is to do rheological properties and after that do 3D printability by comparing the results. But here we're doing the opposite. We are testing the 3D printability and then we are getting the rheological properties of the mixes. Why we are doing that? Because there is no established criteria for polymer concrete, and we are trying to establish a criteria, an acceptance criteria for polymer concrete based on its rheological properties. Like, for example, if we tested for multiple polymer concrete mixes that are printable, the rheological properties, and we put a guidelines like the minimum and maximum, then we can decide for other mixes in the same manner. So here we are deciding, for example, a printability window for 60 minutes. We know that all these mixes are printable at 60 minutes, and we define the minimum and the maximum static yield stress, dynamic yield stress, and thixotropy. To develop a finite element model, we have to get the early age properties of the 3D printed polymer concrete, and which is called, like, we can call it the green strength, and it's the ability of the material to carry its own weight. So the green strength represent a combined of cohesion and friction, and we model it using more column failure criteria, and by doing the direct shear test where we apply a normal load and measure the shear stress. So we have done the test at different time intervals, and you can see, like, between 0 to 30 to 60 minutes, there was no increase in the shear stress. Between 60 and 110 minutes, there was a significant increase in shear stress. And of course, we repeated the test for We repeated the test at another normal load. The same conclusion was observed, like between 60 and 110, we have an increase in the shear stress. So if we plotted the shear stress versus the normal stress, we can find the cohesion and the friction angle. And we found that the relation is bilinear. After 60 minutes, we can find a significant increase in the cohesion. So if we want to divide the, this graph into two categories, the first one from 0 to 60, we can call this a printability window, where we can print in that range. And after 60, it's the structural build-up and the shape retention ability. And this is confirms why at 60 minutes we are starting having this significant bilinear effect. It's because when we test the gelation time, and that's where the polymer change from liquid-like to a solid-like, we find that the peak temperature, and the peak temperature, that's where polymerization happen, is at 60 minutes, 45 minutes. So also we tested the elastic modulus increase with time. This was a struggle here, but we managed to get results because the material was still fresh, and polymer concrete is a little bit sticky, so it was a hustle. But you can see here at early ages we have a bulging effect, and at later ages we started having the normal concrete shear failure. And what I mean in later ages is about 60 minutes, 70 minutes, and so on. Also, for the stiffness increase, we can find that we have a bilinear effect. You can't really see it, but here we zoomed it because from 0 to 30 minutes, we have a significant reduction in the stiffness. To confirm that we have a good structural stability, polymer concrete showed a 60 MPa strand value at 7 days, which is comparable to normal concrete, but we are getting that at early ages. And the interesting thing about polymer concrete here is that we can get a range of youngest modulus. We can get 14 gigapascal and ending with 2 or 3 gigapascal, which can be very useful in application where we need to do vibration dampings. So all the properties that we got was then fed into a finite element model. And the failure were predicted. You can see the stress contour. The stress is maximum at the lowest layer, of course, and the displacement contour. So we 3D printed the tank, the circular tank, to check if the numerical simulation give us the predicted results. And we can see that the numerical simulation predicted a failure at the 10th layer, which we already got in the experimental work. So here is, and then after simulating and predicting failure and everything has been done, we 3D print a full-scale 3D printed polymer concrete structure. Here we are doing it with fiber reinforcements. This can be used in many applications, like in enclosure joints, in accelerated bridge construction, in, of course, architectural, drainage pipe, vibration damping material with a very low youngest modulus and still high strength, manholes, tanks, flooring, and so on. So as a conclusion, polymer concrete can lead the way as an emerging technology in the construction field. A next generation polymer concrete can be developed in a variety of polymer, aggregate, and nano-modified materials. The rheological properties of polymer concrete mainly depends on the polymerization rate, and the time-dependent properties of polymer concrete can be used to develop finite element model, which then can predict failure. So an experimental investigation integrated with numerical simulation can help a successful 3D printing of polymer concrete. Here are some journals directly related to our work. And here are some selected journals from my advisor team, research team publications. You can check them for further reads. We would really like to thank our supportive industrial company, Transport, Aramak, and Epoxy Chemical. They have been supporting our work on polymer concrete for the last 20 years. And a special thank you for Sandia National Laboratory and NEXT ACI for the funds and support of this project and for giving me the chance to participate and present our work. I would like also to acknowledge my amazing team. They have been helpful, and we have all been working on this together. Thank you. Any questions?
Thank you, Siham.